Welcome to a review of useful trig identities. So recall, we have a variety of trig equivalencies that we can use to change the format of functions. So we have a variety of equivalencies in trig that we can use to change the format of a function. So we have our most basic cosine squared plus sine squared equals 1. So cosine squared theta plus sine squared theta is equal to 1. From that, we get the equivalent statements with tangent and with cotangent. So if we divide through by cosine squared, we wind up with 1 plus tangent squared theta is equal to secant squared theta. If we take the original equation and divide through by sine squared, we get cotangent squared theta plus 1 is cosecant squared theta. So these are all equivalencies that we can play around with. In addition to this, another extremely useful tool to have is our double angle formulas. Or half angle, depending on which approach you're taking. So for sine, we have sine of 2 theta is 2 times sine of theta times cosine of theta. So we could have used this double angle formula for evaluating the integral of sine theta cosine theta earlier in one of our previous videos. And then the one that becomes most useful is the double angle formula for cosine of 2 theta. So cosine of 2 theta, we have multiple forms this one can take. We start off with the cosine squared of theta minus sine squared of theta form. But sine squared theta is just 1 minus cosine squared theta. So this is equivalent to 2 cosine squared theta minus 1. It is also equivalent to 1 minus 2 sine squared theta. So what this means then is we can rearrange this. Cosine squared of theta can be rewritten as 1/2 of cosine of 2 theta plus 1, the 1/2 multiplying the entire cosine of 2 theta plus 1. And we have that sine squared of theta is we would have cosine 2 theta minus 1 divided by negative 1/2 becomes 1/2 of 1 minus cosine of 2 theta. These formulas are extremely useful when we are doing integrals because we can lower the power of cosine and lower the power of sine. So these are useful for lowering a power of cosine and sine. So let's do a quick example. Let's go ahead and evaluate the indefinite integral, the integral of sine squared of x dx. So we will just go ahead and swap that sine squared of x out for 1/2 of 1 minus cosine of 2x. So this sine squared of x is just 1/2 times, in parentheses, 1 minus cosine of 2x. So we wind up looking at our integral of sine squared of x dx is just the integral of 1/2 times 1 minus cosine of 2x dx, or 1/2 times the integral of 1 minus cosine of 2x dx. At this point, we can go ahead and swap that cosine of 2x. We'll take that 2x and swap it out for u. So our du is, u is 2x. Our du would be 2 times dx, or dx is 1/2 du. So we now have, this can be replaced as 1/2 times the integral of 1 minus cosine of u times 1/2 du, or 1/4 times the integral of 1 minus cosine of u du. Doing this integral, we have 1/4 times 1 would go to u, minus cosine of u will go to a minus sine of u. And then we have plus c. Plugging back in our 2x. So u is equal to 2x. We wind up with 1/4 times 2x minus sine of 2x. 1/4 multiplying that entire thing, and then plus c. So this enables us to integrate that sine squared of x, whereas otherwise we would have run into trouble if we tried to do composition. If we set sine x as our u, we would not have du in the problem. So this enables us to reduce that power so we can perform the integral in a more familiar integral.